Well, we'll do one of them two different ways to make sure that our approach is legit. And then after that, we'll just kind of ride off into the sunset. So in number 8, we're looking at a single function over a particular interval. Whenever you have a single function and you're looking for total area, you know that you can get away with a single integral. All right, it's just a question of what that integral is going to look like. All right, so this integral would go from 0 to 4. Now, not all of this bounded area is above the x-axis. If I want total area, I want the sum, again, only of positive areas. So negative areas have to become positive, right? So I need a function that will negate the negative part, right? So what's my integrand going to be? That would be the thing inside the integral. Yep. Okay. Now, just so you know it, and because it can be important, you know, with multiple choice questions, you know, which of the following integrals or the sum of integrals could be used to determine the area of the bounded region, the total area. You know, this might be one of them. Maybe they want you to put it in a different form. If that's the case, you might break it up and say the integral, the definite integral over the interval of 0 to 3 of the function itself added to the absolute value of the integral going from 3 to 4 of that same function.
Would absolute value bars differ? Would it mean something different if you put it inside?
No, it works inside or outside. It's the same. In this context. When you're dealing with an ordinary function, like if I did the same thing with this one, it would not be the same thing. Right? So it's only because this entire integral gives a negative result that we can put it on the outside.
So total area is just like all of it, where net area is like area above the x-axis?
Net area is the area from beginning to end, accounting for negative areas also.
Right.
So
Gotcha.
we would subtract this off as well.
And total is just added.
Added all the positive areas. All right, so might as well check this. We got the calculator on. So math 9, actually, let me do it this way. Put my function in, 3x minus x squared. Get rid of that. I'm just typing it into y1 because I know I have to put the function in repeatedly. So instead of writing the function in repeatedly, I'm going to put it in once and then just make use of my y1. All right, so math 9, going from 0 to 4, absolute value of y1, alpha trace y1 dx. All right. So if I actually needed the area, I could get it. I can math frac that pretty easily. All right. But now I want to compare that to the other way of writing it. So math 9 from 0 to 3 of just y1 plus the absolute value, math 9 from 3 to 4 of the same function. Should give us the same answer.
Do you have the same one? Oh, it's 57.
So, I mean, not too crazy to do by hand, but obviously a calculator is a nice, nifty shortcut. Right.
Am I? I don't think that matters.
Yeah, there's no trig in this.
Oh, maybe it's because I did the absolute value. That's probably why.
All right, so in number 8, the area in question is entirely positive, so we're not worried about absolutes. Number 10, you probably can figure out already, because it's pretty much the same as number 8. But number 9, Oh wait, I said number 8, I meant number 9. Number 9, the area is entirely positive, so it's just a matter of figuring out what the area would be under the curve and then subtracting off the rectangle. Right? And you could subtract off the rectangle one of 2 ways. Right? The first way to do it would be to actually find the area of that rectangle. Right? So base times height. So what I can do there first is address the sine function. So on the interval of 0, pi over 6 to 5 pi over 6, sine of x dx minus, now that gives me everything below the sine function, all the way down to the x-axis, right? So I don't want this rectangular region. So I could subtract off the area of that rectangle. The height is 1/2. Right, and that's because of 2 reasons. One, just kind of eyeballing it, it looks like 1/2, but that's not the best reason. The best reason is that y is equal to the sine of x, so the sine of pi over 6 is 1/2. All right, and the sine of 5 pi over 6 is also 1/2. All right. Now that base length would be the difference between 5 pi over 6 and pi over 6. So 4 pi over 6, which would be 2 pi over 3. So the area would be equal to 1/2 multiplied by 2 pi over 3, result pi over 3. So if I take my integral and subtract from it a pi over 3, oops, little stray mark there, that would get the job done. Or I can go pi over 6 to 5 pi over 6, take the sine function, and subtract from it the integral from pi over 6 to 5 pi over 6 of the constant function y equals 1/2. All right, so 1/2 dx, which amounts to the same thing. Now, I would do it this way with the pi over 3 if I were doing it to figure out the numerical answer. But again, be prepared for this, because you never know which of the following choices could be used to determine the area under the curve. Right? But this technique also leads you to the next lesson, which is finding the area between 2 functions. Right? So what this is telling us is that if I ever want to find the area between 2 functions, find the area below the outermost function and subtract from it the area below the innermost function, and you'll have the area between. All right, so that's kind of like the entire next lesson, all in a nutshell.
Aren't you not, like, you still have technically right now that integral would have the sides of the triangle next to the curve shaded too, but they're not shaded.
These two?
Yeah.
Well, that would be if I was going from 0 out, but since I'm starting at a pi over 6.
Okay. Is that, would you know where if it was just a picture, how would you know what your bounds are? Like wouldn't you have to know that it started at pi over 6 and not 0?
Yeah, and that's based on where the shaded area is. Like in the next one, I know it has to go from 0 to 3, because that's where the shaded region is. All right. So speaking of which, this one is just 0 to 3. Absolute, it's the same function throughout, so absolute value of 4 minus x squared, close it up, dx. All right, but now for the more interesting ones. So number 7, we run into a little bit of an issue here. If I were to just integrate the function y equals x squared minus 1, what that would actually give me is the area between that curve and the x-axis. All right, so in the form of a diagram, it's not going to be quite what we want. It's going to give us this. and it's going to give us this. All right, so, I mean, that's something. Something kind of useful, I guess, because what I can do is find the integral from 0 to 1 of x squared minus 1 dx. Then, well, that's negative. I need that to be positive, so I'll absolute that. I can add to that the area of this rectangle here. All right, the base is 1, the height is 3. Area is equal to 3, so add to that 3. Then I can also, I mean, the integral here is going to give me the shaded area that I don't want, the one that I shaded. If I subtract that from the area of this rectangle, then I'll get the area that I do want. So I'll have to add to this. That whole rectangle is still an area of 3. 3 minus the integral going from 1 to 2 of x squared minus 1 dx. All right, which you could clean up, kinda, sorta. Not really. I mean, you could add the 3's together. Yeah, look at that. So that'll do it. But there's a better way. And the better way gets you that area with a single integral. One single integral, and it's a fairly simple integral. Right? It's a matter of perspective. Right? So what's happening here is we're taking, and I'm going to just read, I'm going to rough out a quick sketch of the diagram off on the side. We're going to redefine this function. Because a bounded area, when we talk about a bounded area, we're talking about the area contained between a function and the x-axis, but what about a function in the y-axis? Because here, when we looked at it from the function containing area between itself and the x-axis, it was a mess. But the entire area, if we look at it as it relates to the y-axis, the entire area is bounded between the function and the y-axis. Right? So, and that's actually fairly clean. Actually, let me do that slightly differently. I'm going to take the approach of the Riemann sums, right? The rectangular approximation. I'm not going to actually do all the algebra, but if we were to actually think of this the way we did when we were populating bounded areas with infinitely many rectangles, what we would have, instead of vertically oriented rectangles, we would have horizontally oriented rectangles. So instead of having a thickness of dx, we would now have a thickness dy. Instead of having the length of the rectangle be the height, it's now the length. All right, so we're changing perspective. All right, so instead of it being y, it's now x. All right, so area would be x dy. So as long as I can come up with an x equation, I'll be able to take care of this problem fairly easily. Now they told me that y is equal to x squared minus 1. So what that means, if I clean this up a little bit, is that x, add the 1, take the square root, would be equal to the square root of y plus 1. So it's not quite the idea of taking the inverse, because the one step in the inverse that we didn't apply here would be actually switching the variables. We're not doing that. But we're doing every other step that we would if we were finding an inverse. all we're doing is we're writing another explicit equation, but in terms of y rather than being in terms of x, all right? So when I want to redefine my integral, I could say, or the integral of the square root of y plus 1 times dy, square root of y squared plus 1, square root of y plus 1 dy, that product gives me the area of a single rectangle. Integrating gives me the infinitely many rectangles that I want added together. Now I just need to know the bounds. Where does the bounded area start and where does it stop? -1 to 3. So one simple integral as opposed to one not so simple integral, set of integrals. Okay, so let me just, it's not a proof, just a demonstration. Okay.
Two questions.
Sure.
One, why can't you just shift the whole graph up one?
You can, and then what you would still have to do though, because you're gonna get the area under the curve, you would still have to subtract it from a rectangle. So you could shift the graph up 1, which is gonna change your function, so keep that in mind.
Yeah.
It's also gonna change your bounds, but you're still gonna get area under the curve, so make sure you subtract it from the rectangle and it'll still work.
Okay.
Yeah, transformations are always a good thing to consider. So I'll use my little simplifying step here. I'll do the +6 minus math 9, 1 to 2, x squared minus uno dx. All right, assuming I typed it incorrectly, we should get an area of about 5 1/3. Now let's see if it works out the other way. Now you could still, when you're typing this integral in your calculator, you could still use x's, but if you want, you could use y's too. Sometimes it's more satisfying that way. So -1 to 3, the square root of y plus 1. Just as long as whatever you type in your integrand is consistent with what you type in after the d. All right, then everything's gonna be fine. A little variation at the end, but they're these things. Because the calculator doesn't do calculus to figure all this stuff out, so sometimes there is a little wiggle. All right, but the good news is, the great news is, when you look at something like number 11, you don't have to bother with all that other stuff in terms of thinking about it, in terms of subtracting from rectangles, although you could. In this case, it might actually be slightly easier than number 7. What you really want to be thinking about is changing your perspective. You want to be asking yourself, you're asking yourself 2 questions. Is the bounded region entirely adjacent to the x-axis? Is it entirely adjacent to the y-axis? Whatever the answer that gives a yes, whatever question gives a yes as an answer, that's the perspective you want to use. All right. So in this case, it's entirely adjacent to the y-axis, so my perspective should be with respect to y. It makes it seem at this point that it's a choice. There will be situations where you have to do it this way. So if you have it in your mind, like I did when I was a student, that, well, I mean, it's fine that you're showing us, bless you, this new technique, but I'm not going to do it that way. I like the other way. It's not a question of like. It's a question of, you won't be able to get some questions right if you don't do it this way sometimes, so just bear that in mind. Some questions are just not doable with respect to x, so you do have to change your perspective. All right. So once I draw, I personally, I like to draw the rectangle in there just to make sure I have the perspective down. I know dy is accounted for, but x is what I'm looking for, and x is a function of y. Sometimes people, I've seen this before, I don't write it very often, but people will write it like this, x of y, to remind themselves what x is. because they'll be looking at x and be like, okay, well, what's x? Is it 2? Is it 10? Is it a number? When you write it like this, it's a reminder to yourself that you're looking for a function of y, x as a function of y, which should steer you to this guy and tell you to solve that for x in terms of y. All right, so we're looking at 3x squared equals 3 minus y. And just swap them. X squared is equal to 3 minus y over 3. Since we're doing it on the calculator, not overly concerned with simplifying. 3 minus y over 3 under the root. Now, I glossed over it in the last question, but I'll mention it here. When you take a square root, it should be plus or minus. But since both of the bounded regions, the one in 7 and 11, are on the right-hand side of the axis, you're only dealing with the positive.
Shouldn't it be
Over
over -3?
negative 3?
If you flip the 3 minus y, you make it
Oh,
equal.
okay.
Yeah, I did a switcheroo here. All right, so the old switcherooski. So from -9 to 3, my x function, 3 minus y over 3 dy. And that would get us our area, if we were so inclined. Bless you.